Hi, it's Robin. There's a lot of times that I write a little program like print peak 56320 just to print the value of the joystick port, for example. And then I run it and make sure that I get a different value for each direction and for the fire button. By the way, thanks to my patron Carsten for making me this pretty amazing joystick, this custom build, 3D printed, seems like a beautiful joystick. Just received it. I'll probably look at it in more detail in a future video. But rather than printing in decimal, it would be helpful to me to print this in binary, because rather than just, seemingly a random series of numbers, not actually random, but then we could see the individual bits change. Like when you push up, that's a difference of 1, and that would be the rightmost bit that would change from 1 to 0 when you push up on the joystick. And each of the 4 directions each have a bit. 1, 2, 4, 8 is their value, and 16 when you press fire, corresponding to 2 to the 0 all the way to 2 to the 4 in the binary values. So I wanted to print a binary value, and I thought there would be some basic extension like the Simon's Basic cartridge that I could plug into the C64, but no, that didn't have a binary print. I looked at Commodore 128 and +4 Basic. Those also didn't have a binary print. Actually, I looked quite a few places, and there was no simple plug-and-play solution. So I thought I'd program my own binary print routine. That's what I did first in BASIC, and then I went down this, rabbit hole of optimizing, trying to come up with the fastest routine, and then I ended up writing it in assembly language. So we're going to go through all those today, and you can see the steps I took. Okay, so there'll be a D64 linked in the video description if you want to try any of these out for yourself. So for this, the first thing I did was make kind of a benchmark framework, and here it is. It's just a pretty short program. I'm just using colons as a form of like a blank line for a bit of white space. And all the program does is clears the screen and sets the cursor color to white. Then it sets the system timer to 0. And then it's going to just be a loop from 0 to 255, a full 8 bits of value. And we'll just assign the variable a to whatever x is, so that the particular decimal to binary conversion is free to do whatever it wants with variable a. It can modify it or whatever, but x won't be changed because we don't want the program modifying the main control loop. Then it just prints out the current value of a with a comma just to move to the next tab. And then here at line 200 up to 900 is where our actual conversion routine will go. Just for the benchmark, I'm just printing a string of x's, but that's going to be the 8-bit binary value. And I do want to preserve leading zeros, so it's of a fixed width, a fixed 8 digits. And note that I'm going to try and keep just one statement per line when possible. Once in a while, to implement a certain kind of algorithm, I may have to put more than one statement on a line occasionally, just because of the limitations of Commodore BASIC. But the goal is to have fairly readable code as well. Just seemed like it would be tiresome to try and read hyper-optimized code with all the white space removed and so on. As long as I do that consistently, then it should be fair. Again, you're welcome to optimize these further if you want to. And then the next iteration of the loop, and at the end, it prints out TI, which is the number of jiffies or 60ths of a second divided by 60. So it'll just print out the number of seconds that the benchmark took to run. So just to see the framework running, it's just going to print the values from 0 to 255, and where those x's are, that's where we want the binary conversion. And at the end, it'll print our time. So with no actual conversion, it takes about 12.5 seconds to run. Basic 2. So again, framework is the same, and what we've modified here is these lines between the colons here, so lines 200 through 260. And this algorithm is one I found online. I figured, oh, somebody's probably solved this problem before, so I did a Google search, and not very much came up, except there was a thread on Lemon64, and this is adapted from a post by E5Frog. I think the code's more or less the same, the algorithm's the same. So I'm going to roughly work through a whole bunch of different things in increasing order of efficiency. So this is basically the worst one I found, but no offense to E5Frog. It's great that E5Frog put their code out. Okay, so variable D starts at 256, and then we're going to do a loop 7 iterations. Again, this is converting decimal to binary. So each step through, we're going to divide D by 2. So the first iteration, it'll become 128, and then B for the bit is the input variable A divided by D, and you take the integer of that. So it'll be either 0 or 1 after this division, and then it will simply print out that bit, and then from the number that we're converting, that's A, we're going to subtract that bit times its value. So in this first iteration, it'll either subtract 128 or 0, and then it'll do the next loop. So 7 times, we go from 128 divided into it, 64, 32, and so on, and then subtract the value of that bit if it's there. So A is just shrinking, and then after 7 iterations, all that's left is the remaining value, which is either 0 or 1. And you end up with a binary value, so let's run that and see what happens. So you see one big drawback here. It's actually printing extra spaces, and that's just a consequence of how Commodore Basic handles numbers. It just always does print spaces in between each number. So that's not ideal, and we'll get rid of those in the next iteration. By the way, I'm just going to jump ahead. You'll want to watch all these scrolls in full, I think. So I will fast forward. Okay, so in total, 52.95 seconds. I'm sure we can do better than that. But the first thing I want to do is just get rid of those spaces. So basic 3 just has 2 extra lines here for each value that's going to be printed. That is the B. Instead, we're just going to print the rightmost value, and that eliminates those spaces we don't want. And we have to do that at the end of the algorithm as well. So we can run that. And it probably comes as no surprise that that slows it down even more. Okay, so that took 58.78 seconds, but at least it eliminated all those extra spaces. So the output's what we want. That's just much slower than I would like. So I made a new version. And here's the new algorithm. Instead, we start with a base value of 1, and we're going to work backwards through the bits from the high bit of 7 down to 0. That's because we want to print the high bit, which is the leftmost bit, first. So that's just this loop here. And at each iteration, we're going to take the current I, starts as 1, multiply it by 10, then we're going to do a logical operation between A, the input, and a logical AND with 2 to the power of B. So when B is 7, 2 to the B is 128. So we're going to test that leftmost bit. And if the value of that is greater than 0 or non-zero, this clause here returns a -1. So that's why we have a minus sign here. That flips it to +1. And either 1 or 0 is added to this base value. So what we're doing is building a decimal number that only consists of 1s and 0s. keeps multiplying by 10, which has the effect of shifting this decimal number to the left, making it 1 digit bigger, and then adding a 1 or a 0. So we have a decimal number consisting only of zeros and ones. So essentially it's a binary looking number, even though it's actually a decimal number. And then at the end, we just print the rightmost 8 characters. So the reason we start with 1 and then it goes to 10, 100, 1000, plus any extra ones along the way. The reason we do that is so that the resulting number will end up with a 9-digit number starting with a 1, and that preserves the zeros to the right of that. Even if we have leading zeros, they won't be removed. Normally, decimal would remove those numbers. Okay, so we'll run that. Well, it probably comes as no surprise. This is even slower. Whoa, 96.85 seconds, even worse. Way worse, in fact. So, we need a different approach. So, time for basic 5. So, for this one, we're going to start cheating a little. And by cheating, I mean we're going to pre-calculate some values to speed up the later calculations. So we're going to make 2 arrays, just one-dimensional arrays. One is called B, and that's just the value of each bit. So we're going to iterate from 0 to 7, and for each one, we're just going to make an array where the array indexed by B, these are different variables, by the way, because it's kind of confusing, but actually I find it more intuitive to say, well, the B array stores the value for each B bit, and it's just 2 to the power of B. So B0 will equal 1, B1 will equal 2, all the way up to B7, which will equal 128. So those are pre-calculated, so we just have to do the array lookup instead of the actual exponential math each time. And we're going to do the same for I, where these are, I suppose, I for integer. Each one is 10 to the power of I. We're still using that decimal technique, but we are pre-calculating the multiplication by 10. The pre-calculation isn't included in the benchmark. I can go either way on that. What I really want is the fastest printing. And if there's a bit of pre-calculation needed, like a one-time precalc needed at the beginning, then it seemed to make sense to me to not include that in the benchmark, because what I really want is a very fast binary print, even if there's a bit of pre-calculation needed one time. If you don't like that, you've got the code here, you can rearrange it how you see fit. Okay, so the rest of the framework's the same, and then this is the new algorithm. So we're going to start off with the value of 100 million, that is 8 zeros and a 1 at the front. And again, maybe this will make that idea more clear. This is a decimal number that represents a 9-digit binary value, and the goal here is just to use the rightmost 8 digits. And the reason we're putting that 1 as a placeholder so that the leading zeros are not removed as they normally are with decimal numbers in Commodore Basic. And again, we're going to work backwards from bit 7 down to 0. And now the only compare we need to do is if the input number with a logical AND, this returns 128 the first time. Again, we're using that array lookup instead of the more computationally expensive 2 to the power of B up here. Then all we do is add I equals I plus the corresponding decimal value of that bit being set. So that would be 10 million. So basically, if bit 7 of the value is set, then we're going to add 10 million, which is 1 followed by 7 zeros. And this is a much quicker algorithm, and at the end, we just print out the rightmost 8 digits again. So So let's run that and see if it's faster. You saw the short pre-calc time at the beginning there. Maybe just a second or so. Okay, that's a big improvement. 35.9697 seconds. Huge improvement over whatever we had, 95 last time. Okay, next up is Basic 6. Let's look at that one. So this is a different approach. We're still going to pre-calculate the bits, just the one array. And here's the new algorithm. Again, counting down from bit 7 down to 0, step -1. But instead of doing all that decimal math, we're just going to convert directly to a string. We test each bit to make sure it's non-zero. And if it is, then we print 1 and continue the loop. Otherwise, we test if the loop is still valid. We're actually testing B here. And if it's greater than or equal to 0, then we're going to print 0 and continue the loop. Otherwise, we just print a new line and then continue on to the next value. This extra if was necessary to test that the loop is still active, because when the loop is done, B will actually be -1, and that's when we want to follow through and exit. That was a little bit tricky. So let's run that. Pretty zippy. Okay, 35.93 seconds. So just a tiny bit faster than the previous one, but I think we have more room to improve this. So another improvement we can make here, it's actually unnecessary to compare to 0. If we just go A and B, this will actually evaluate as true, and that's a bit of a savings there. And run. Okay, so now we're all the way down to 31.4 seconds, about 4 seconds faster. Getting down to the last few here. So this is very similar to the previous one, but I realized that after the for next loop is over, it will actually execute another command on the same line. So what I did was added a GOTO 230 to go to that final print, and that eliminated the necessity of having that extra check for B to make sure that B is greater than or equal to 0 to print a 0. So there was another optimization, and I'll run that one. Okay, so all the way down to 28.4 seconds, another 3 seconds of savings. Now with Basic 9, this one's getting kind of ridiculous. So again, just the same pre-calc at the beginning, just the one line to make that bit table. But we'll look at the whole program here. So this is like the most code in the main algorithm that we've done from lines 200 all the way to 310. And this was kind of a dumb idea, but I gave it a try. So what we're doing here is a shortcut where normally we would want the for next loop to go from 7 to 0. So we set it to 7 here, and I'll get to all these lines of code, but basically we set to 7, and then 280 through 300 are the same code that we just saw, just doing the for next loop from 7 down to 0, all the same optimizations here. But there's this extra set of optimizations where we check if the value of A is less than 3, then we know well, that's buggy. Okay, whoops, I just noticed I had all these values off by 1. You guys, again, are the rubber duck I talk to and find my own bugs. But basically the idea here is this is an optimization where if A is less than 2, that is if it's 0 or 1, then we know there's going to be 7 leading zeros, so we just print all those and then set B to 0 so that only the last iteration of this loop has to execute, and it'll print either the final 1 or 0. And likewise, if A is less than 4, that means it's 0, 1, 2, or 3. That means we know there are 6 leading zeros and B equals 1, and so on. I had these all off by 1. There were several errors. So the reason I'm using a less than symbol is just because it's slightly quicker to parse. Yes, I could do less than or equal to 1, but that's slightly slower to parse. So, okay, so that's the optimization there. Again, basically the same as the previous one, except it has all this extra logic to try and save some time. Okay, will it work? Okay, 33.63 seconds. Unfortunately, that added about 5 seconds to our time. Maybe some combination of these would actually be a time saver. So as much as this saves some time here, the cost of doing all the comparisons outweighs the benefit. Okay, and the final basic version will list this. Whoa, it doesn't even fit on a screen. So what we'll do is look at the first section. We've added a huge pre-calculated section. So this is the regular calculating B, the value of the bits. But then we're going to make an array called B string. That's 256 elements. These are zero-based arrays. 256 elements in length. And we're going to go through and we're going to pre-calculate the 8-digit binary string for all 256 values. Isn't that terrible? So we just go through here, and this is just a variation on the previous algorithms. We're building up the binary string 1 digit at a time. So the string B string is the binary representation of whatever A currently is, just going through from 0 to 255. And then we assign it to this B string array, so it's all pre-calculated. You notice that I did set the system clock to 0 for the pre-calculation. The calculation was going to take so long that I thought it was only fair to actually show how long it takes. And then we just set PT to the pre-calculated time. And then just look at the rest of the program. Now all the rest of the program requires, all this framework is exactly the same. Now that we've done all the hard work ahead of time, all we have to do is print B string indexed by A, and it does the binary conversion. And then here it's just going to print out both the pre-calculation time and the actual time like normal. Terrible. Does it work though? That's a pretty long pre-calc time. And here it goes. I'm just going to let it run in real time for once. Look how fast that is. This is not fast forwarded. Woohoo! So actual printout time, 13.16 seconds. Over 20 seconds of pre-calculation time, but in total, that's about 34 seconds, even including the pre-calculation time. So that's fairly competitive, even if you include the pre-calculation time. And then after that, you can do unlimited binary conversions at a very fast rate. What is that, about 20 a second? Pretty fast. Okay, I understand if you think that's cheating, but it is all just pure basic. And that's the fastest way I could think of. But if you really need speed, of course what you should do is program in assembly language. So that's what I've done. So this is on that same D64 file. Load temp, %sign is the same as loading .8, .1, sys 32768, back arrow L to load binary.s is the source file. And let's walk through it. Again, I'm assembling to the cassette buffer, just because it's quite a small program, at 828. You could put it elsewhere in memory if you like. So if you haven't already seen my video about adding parameters to sys commands, then I recommend you watch that one, because I'm not going to fully re-explain everything here. Okay, sys 828, the value that you want to print. And just because it was easy, I actually allow up to unsigned 16-bit decimal value to be passed in. And then B is the number of bits starting from the least significant that you want to print. If you leave this parameter off, including the comma, then it will default to 8. And I'll show you how I did that. I'm just going to use 3 0-page locations, the 16-bit formed by FB and FC, and 8-bit length of FD, but really the maximum length that is supported is 16 for a 16-bit value. These are the 3 built-in basic routines that help parse the sys command. And again, I went to that in the previous video. And here we're going to get the value that we want to print in binary just by calling this read param subroutine. That's identical to the previous video where it just calls these 3 routines. Skip comma, when parsing it jumps ahead, it skips the comma. Then it evaluates the parameter. So you could just have like a constant number in there, or you could actually have a parameter that needs to be evaluated, and then converts that value into a 16-bit unsigned value. After calling those routines, the low byte of the value is in Y, and the high byte is in A. So we just store that 16-bit value into value. Then this is something I haven't done before, but I wanted to make the number of bits default to 8. And it's actually pretty easy to do that. After we've read in the value, we just have to check if there's a trailing comma. So we set the Y index to 0, and this location 7A points to the next character that's going to be parsed. And we're going to set a default of 8. Then we're going to compare the accumulator and see if it's the same as the Petsky for a comma. And if it is not equal to a comma, that is that there isn't a trailing comma, then we're going to branch ahead to default. Otherwise, we are going to read in the parameter, the length in bits, and either way, we're going to store Y in length. The reason the order is a little bit convoluted here is because that saved extra compares. It simplified the logic. If I was to load Y with another value, then I would have to have an extra branch or two to cover for that. So either way, 0-page location len is set to the number of bits we want to print. Default of 8 or whatever number was included. I don't do any extra error checking here. You're welcome to add that if you want to. And now we're going to go through processing all 16 bits. So because we have a 16-bit value, we're going to iterate through all of them, but we're only going to print the rightmost bits as specified by length. We're going to start bit 15 at the left side of the 16-bit value. And now with 16-bit value we have, we're going to arithmetically shift the low byte to the left, that is multiply it by 2. The high bit will fall into carry, then the carry will be rotated into the high byte of the value, and the high bit will fall off. The 1 or 0 at the leftmost side of our 16-bit value is what we want to print first and is now in carry. So all we have to do now is load the Petsky value of 0, and then if we add with carry 0, it'll just add whatever carry is. So we'll end up with the Petsky for either 0 or 1 in the accumulator. And now we have to check, are we actually going to print this value? We're going to see if our Y index, which is starting at 15 and working down, we compare Y with the length. If carry is set, that is, if it's greater than or equal to, then we do not want to print. So with Y starting at 15, 14, 13, 12, we only want to print any value that is less than the length. If it defaults to 8, it's not until we get down to bits 7 through 0, less than 8, that we actually want to print those values. We just branch ahead to here if we don't want to print, but otherwise if we do want to print, we just jump to subroutine FFD2, which prints out the character. So it's actually up here that we're setting up the accumulator with the character we want to print, but we're only deciding whether we print it or not down here. And again, I did that to save some branches. In a way, it would be more efficient to branch, then figure out what character we want. But the problem is that this is where we got our carry from, but this comparison actually destroys carry. So then we would have to save carry somewhere, or we could push it on the stack. Anyway, I tried that and it got really confusing. So I far prefer this straightforward approach, just linear with as few branches as possible. Okay, and then we decrement Y to see if we have processed all 16 bits. If Y is still 0 or greater, that is positive, then we're just going to go back up and loop again. Otherwise, we're done. Return. So that's it. Back arrow 3 to build. Back arrow 1 to escape to basic. And we'll load basic 11 and we'll look at it. This is the same framework, but you see there's no pre-calculation needed as long as the machine language is in memory. And now we're just going to call sys828 with whatever A is, the value we want to print. And we're not printing a new line in the machine code. I didn't want to assume I'd always have a new line after every time I print a binary value. So we just need an extra print to go to the next line. And that's it. And we could optionally choose how many bits we want to print here, but we're just going to go with the default 8. Okay, let's see how fast the machine language version is. Okay, 13.68 seconds. So that's actually about half a second slower than our basic version, which I found was pretty funny. And I thought maybe that extra print was causing the problem. So I'll have it print the carriage return here in the machine language. And I can get rid of line 210 now, because we don't need that print now that the machine language is doing it. Does this make it faster? So still 13.6 seconds. So kind of incredibly, the all basic version with the pre-calculated strings is even faster than the machine language version. Mind you, it's still being run in this basic framework and it's being called with the sys, the SYS. Just goes to show how fast basic printing really is. It really is like machine language speeds, where just the time to parse these values here and in the machine language takes longer than printing those pre-calculated binary strings. Now, maybe there's some way of making this even faster, but I wouldn't want to sacrifice the flexibility so badly that I can't even just call this command like this. So how about that? Pre-calculated strings wins. Okay, just to wrap it up, let's give that joystick a try again. Here we go, sys828 peak 56320. And then we just got to print a new line and go to. And let's try running that. Oh, I forgot that I left that in there. Okay, run. Let's try it. There we go, yay! So up is the rightmost bit, down is the second from the right, left is the third, right is the fourth, fire button is the fifth bit. Actually, because those other bits never change, I can add that third parameter. I just want to print 5 bits. There we go. We can have 3 bits set to 0. Two directions on the diagonal and the fire button. Well, by the way, this is an auto fire button here. So you see how it toggles? And Carsten put in this potentiometer here to affect the rate of fire. Well, it's actually hard to get a good value dialed in BASIC. Kind of goes in waves. So I think that's kind of BASIC's fault. Maybe the interference of the system IRQ causes it to kind of come in and out of sync, and a game programmed in machine language, which is a very consistent 60 Hertz, would be better in sync with the auto fire circuit. Anyway, I think I'm going to do an episode about auto fire sometime, and we might explore this more. That's pretty consistent. It's just not as fast. Oh yeah, and actually rather than holding that down, he put this fix button. You can just hit that one, and you don't even have to hold it down anymore. Thanks very much to Carsten for this joystick, and I'm glad to have this binary print routine. I'm not even sure what I think one of the things I wanted to do with it was hook up to joysticks and for auto fire and so on. Thanks to my patrons for their support. Thank you for watching, and we'll talk to you next time.